The universe goes to that small and then stops. It's like, I'm done. I'm out of here. This is way small enough. I ain't doing nothing smaller. Okay. And then what they did is they went and see how many of these Planck's lengths, right, would fit in a centimeter cube of space, to try to renormalize the infinite density of the vacuum, to get a closed number. So they stacked the Planck's length into a centimeter cube of space, basically, and calculated that the density of the Planck's length would have to be 10 to the 94 grams per centimeter cube. 10 with 94 zeros of these Planck's length in a centimeter cube of space. Well, now they had a finite number. But what is that finite number? Let me give you an idea. If you took all the stars we observe in the universe with the largest telescope on Earth, actually off the Earth, the Hubble, and you stuck, and we see 100 billion galaxies. Each galaxy has over 300 billion stars in it. Most of these stars larger than our solar system. Okay? And you took all that stuff with a huge trash compactor and you squashed it into a centimeter cube of space, you still would not have 10 to the 94 grams per centimeter cube of density. You'd still be short. Okay, so you guys got a finite number. It sounds pretty infinite to me. Maybe we should learn to deal with infinities instead of trying to renormalize them. Because, you know, people got Nobel Prizes for this. So 10 to the 94 grams per centimeter cube is actually what's called the vacuum fluctuation density in quantum space. Meaning that the vacuum is not empty. It's extremely dense. But why does it feel like the vacuum then? It doesn't feel so dense either after, you know, a night at Burning Man. With what happens there, you know, how can the vacuum be so dense? Well, if the vacuum is everywhere and infinite in nature, then it's in perfect equilibrium. And if it's in perfect equilibrium, there's no way you're going to feel it. It can have infinite forces in it, but if it's in perfect equilibrium, you're not going to know it's there. Just like a fish inside the ocean, in the water, will never know it's in the water until you take him out of the water and it feels a different density. We have no way to feel a different vacuum. So we think of the vacuum as empty, when actually it's full. And you can come to those conclusions yourself by simply realizing that if everything is radiating in the vacuum cannot be empty. So I was, you know, amazed, and I'm like, okay, well, let's go with this. the universe is expanding, the vacuum is contracting to infinity, and all of reality emerged from the feedback between expansion and contraction. It becomes really clear then that the expansion part would be the electromagnetic radiation part of the universe, and the contractive part would be the curvature of space-time and the vacuum energy going towards singularity at the center of the system. So, yeah, I'm going to elaborate on it. It became really clear, well, basically, that if there is an expansive and a contractive part of the universe, the expansion part is what we see as reality, which is the radiating electromagnetic emission that we see. A star, a planet, an atom, all radiate energy. That's why we see it, right? And the contractive part that we don't see would be the vacuum energy curving, space-time curving into it, generating singularity, generating the gravitational field. So now I had an inkling about the relationship between electromagnetism, radiation, and gravity.
Gravity goes into the singularity.
Gravity going towards singularity. Space-time curving towards singularity. Now, I later realized that that wasn't that outrageous of a thought. Because when Einstein wrote his field equations, he didn't solve them. Einstein just wrote the expressions. It's 10 differential equations. He couldn't solve them. A physicist that was fighting on the Russian front, right, while dodging bullets, was working hard at solving those equations after they were published. His name was Karl Schwarzschild. And he generated what's called the Schwarzschild solution. As soon as he solved Einstein's field equation, he sent a paper to Einstein with the results. And Einstein presented it to the German Academy of Science, and it became the first solution to Einstein's field equation, which we still use today. Karl Schwarzschild died 2 weeks later on the front and never had time to give further complexity to his solution. Basically, he did it without rotating the field. At first, he was trying to estimate, so he didn't have a rotating metric. And we'll see a little bit more about that later. But the first solution to Einstein's field equation was a black hole. It's called a Schwarzschild singularity. It made a black hole. But because when you go towards singularity with Einstein's field equations, they go to infinity, nasty infinity, that part is ignored. It's called the unsolved nonlinear part of Einstein's field equation. So we use only the weak part of the gravitational field. The part that's not curving very much towards singularity. The part that's much weaker on the outside of singularity. You guys see where I'm going with this? Oh my God. Big omission.